All right, so now that we've talked about kind of all of the subatomic particles and things within the atom, all of Unit 2 is now talking about our bonding, okay? And so multiple atoms bonding together. So whenever we talk about chemical bonds, we always talk about electronegativity, okay? So electronegativity is always going to be used. The reason why is that the electronegativity, right, is how much the atom is pulling on the electrons from a different atom, okay? So it's how much pull that atom has on the other electrons. Really, we can qualitatively understand this using Coulomb's law and using Coulombic forces. Okay, along with our electronic structure. So in general, right, we say that fluorine is the most electronegative. It's going to pull on the electrons the most, and as we move across the periodic table, electronegativity increases, and as we move up the periodic table, the electronegativity increases. So we can use that general idea along with our understanding of why electronegativity is like that to understand the different types of chemical bonds. So our first type of chemical bond is just a nonpolar covalent bond. This is where essentially there's equal sharing. Of the electrons. So if we have the same element bonded to each other, there's going to be equal sharing because those two atoms are going to be pulling equally on the other electrons. So an example of this would be like H2, right? This hydrogen, one hydrogen here, one hydrogen there, they're both pulling the same amount on those electrons. A polar covalent bond, however, if we look at the electronegativity values, we'll see that above 0.4, so or 0.4 up to 1.4, within that range, we see that one atom is really pulling on the electrons a little bit more than the other. They're still sharing electrons, but it's unequal. Okay? So one atom is pulling on the electrons more than another. So this would be like a carbon-chlorine bond, where chlorine is much more electronegative than carbon is, and so it pulls on the electrons a fair bit more than the carbon atom does. An ionic bond, however, the electrons are going to be completely stolen, okay? So essentially they're not shared at all. The electrons are moved from one atom to another. The atom either loses or gains the electron. And there's a very large difference in the electronegativity, so above 1.4 or even higher than that. Generally, right, ionic bonds are a metal and a nonmetal. And the metal loses the electron, the nonmetal gains the electron, and they're really not shared at all, okay? The last type of bonding that we talk about is actually metallic bonding, and this is where the metals just don't really want the electrons at all, so the electrons are able to kind of move about freely, okay? So we have delocalized electrons, right? They don't have one area, one locale that they are in, and the electrons are able to move about freely. So this is obviously between a metal and a metal. Ionic is generally between a metal and a nonmetal, and then our covalent bonds are between two nonmetals. So a polar covalent would be two different nonmetals, and nonpolar covalent would be the same type of nonmetals. that are bonded together, okay? So if we have these different types of bonds, something to remember about it is that really it's a spectrum. We have certain bonds that would be between a metal and a nonmetal that kind of fit some polar covalent characteristics, right? And so it's a spectrum from totally equal sharing to totally unequal sharing, and these are kind of just our general trends where it's a metal and a nonmetal, or two metals, two nonmetals. Okay. But then if we start to look at our bond length, the easiest way for us to look at it is actually to make a graph. Okay. So we have potential energy. That's going to be on this side. And then this is going to be our bond length, okay? And really it's going to be the internuclear distance. Okay, so this is the distance between the nucleus of atom 1 and the nucleus of atom 2. Okay, and so I'm going to put my 0 point up here actually for my potential energy. And when the atoms are really far away, right, if those two nuclei are really far away, they are not really, there's no potential energy that is gained or that is lost because they're not really interacting. The nuclei really aren't interacting, so there's no potential energy that is gained. When the atoms or the nuclei are really close together, right, we would have two positive charges that are getting closer and closer together and are right on top of each other. So that's actually costs a lot of energy, and it's going to be up really high here. But as we move from far away to closer together, we see that the protons in the nucleus of one atom get to interact with the electron cloud of the other nucleus. So we get this interaction, right? We get this interaction that is positive, that is useful, that brings the potential energy or releases potential energy, right? That's the reason that we have a chemical bond, is that we have a positive interaction, or we have a positive nucleus and a negative electrons, and we start to get this good interaction without the bad interaction from the nucleus and the nucleus. So as we get closer, we start to see that it dips, that the potential energy dips down, and there's going to be some point where it is most stable. And that is what our bond length actually is. That's where our bond length is going to be. So then as we move away from that, or as we move once we hit that lowest point, that is where the bond is relatively stable, and that's going to be our internuclear distance. That's our bond length. But as we force the nuclei even closer, this is when it starts to become really positive, and so then the atoms would have to give up energy to be that close together. They don't want to give up that energy, they want to gain that energy as potential energy, okay? So it depends on the size of the atoms, and it depends on the distance between those two atoms, okay? And then it also depends on the type of bond that we have. Single bonds, double bonds, or triple bonds, okay? So this would be just like a single bond, and that could be like a fluorine-fluorine bond or a hydrogen-hydrogen bond, okay? Hydrogen, if we look at hydrogen, right? Hydrogen we know is going to be much smaller even than fluorine, right? Fluorine is real small, but it's going to be larger than hydrogen. So our fluorine would have to be slightly further away than the hydrogen, right? We would say that this bond is going to be shorter than our fluorine-fluorine bond. So that would mean that our internuclear distance, maybe for fluorine, the lowest energy point is going to be further away than our hydrogen, okay? So maybe this one is our fluorine-fluorine bond. This one here would be hydrogen-hydrogen, okay? But as I also said, it depends on the bond order, okay? So if we compare a fluorine bond to an oxygen bond, oxygen has a double bond in it, right? Oxygen is O2 and it has a double bond between those two atoms. So what's going to end up happening is it's going to be closer for oxygen, right? Those two, they're bonded together. They're going to end up being closer together. The internuclear distance is going to be closer together, but the bond is also stronger, right? We know that the double bond is stronger than a single bond. So the potential energy is actually going to be lower down than the fluorine-fluorine bond, okay? So we might have something like that. And this down here would be our oxygen-oxygen double bond, okay? Those, we'll come back in a second. So we have, when we have a single bond, right, it's going to be weaker than a double bond, which would be weaker than a triple bond, and that shows up in our potential energy graph. So a double bond is going to be lower or is going to have a lower potential energy, meaning that it's more stable than a double bond, which is going to be more stable than a single bond. And our single bond is going to be longer than a double bond, which is going to be longer than a triple bond, like nitrogen. Okay? So our single bond longer than double, longer than triple, and a single bond would be weaker than a double, which would be weaker than a triple bond. All right.